Hello, my name is Sung-Hoon Sun. Today, I will present this paper. The paper name is Effects of Brush-Anode Configurations on Performance in Electrochemistry of Microbial Fuel Cells. This paper was published in the International Journal of Hydrogen Energy in 2017. The order of presentation is Introduction, Materials and Method, Results, Discussion and Conclusions. Introduction. A microbial fuel cell, MFC, is being developed for energy-positive wastewater treatment system for generating electricity from organic waste stream by treating detrimental pollutants in it. For practical implementation of MFC for bioelectrochemical wastewater treatment application. Increasing power generation is crucial because it is closely related with energy production rate and wastewater treatability. MFC performance can be enhanced by simply changing anode location. For example, power increases with decreasing distance between the anode and the cathode in general. However, in an extremely close distance, oxygen diffused from the air cathode can be detrimental to anode performance, so that overall power density could be reduced. But, it is still not known which relative arrangement of an anode to a cathode gives the best performance of MFCs. In MFC, various carbon-based materials have been used as anode materials, such as carbon felt, carbon paper, brush type and etc. Among these materials, brush anode is often used. The brush anode of MFC is made up of a titanium current collector for facilitating electron transfer and carbon fibers for holding high amount of microbial communities. It is necessary to quantitatively describe the relative positions of the brush anode and the cathode in order for efficient arrangement of the brush anode to improve power production. To this end, we need to know an electrochemical reference point of the brush anode. At present, it is not known which point is good for an electrochemical reference point of the brush anode. Thus, the following research was conducted in this paper. First, the vertical and horizontal arrangement of the brush anode and relative distance between the electrodes were varied, and the performance and electrochemical characteristics of the MFC were analyzed. Second, found electrochemical reference points of the brush anode and the relative arrangement of the brush anode for maximizing MFC performance. Third, relationships between relative arrangements of the brush anode and electrochemical parameters were quantitatively described. Materials and method. The MFC reactor was constructed from polycarbonate cut to produce a cylindrical chamber 4 cm long by 3 cm in diameter. A brush anode were made from carbon fibers twisted between 2 titanium wires. Before using brush anode was heat treated 450 degrees for 30 minutes in a furnace. Air cathodes were made of stainless steel mesh spread with the 300 mg of activated carbon powder, 30 mg of carbon black, and 1 ml of 10% PVDF solution of the catalytic mixture. Medium for MFC operation contained 10 mmol of sodium acetate in a 50 mmol phosphate buffer solution. A GAGCL reference electrode was installed very closely to the bioanode and used for electrochemical measurement. To investigate influence of relative configuration of an anode to a cathode on performance in electrochemistry of MFC, 5 different anode configurations were tested. The anode core rod was placed horizontally to the cathode in 12 mm, H1, and 28 mm, H2, and vertically to the cathode in 1 mm, V1, 6 mm, V2, and 11 mm, V3. The same bioanode was used throughout the experiment. As a preliminary test, a separator effect on power generation was performed in the other anode configurations, and power densities decreased. Since one of our goals was to find the best anode configuration for increasing power production, a separator was not added except for the H1, where a separator was inevitable in order to prevent short circuit. The cell voltage was recorded at 1-minute interval using a system switch multimeter. Polarization curve test and electrochemical impedance spectroscopy, EIS, measured the experiment using ZiV SP1. For polarization tests, the MFC reactor was operated in open circuit for 90 minutes, and its circuit was connected to ZiV SP1 with the following programming. Rest time 30 minutes, scan rate 1 mV per second, potential range from OCP to 0 volt. EIS measured anode and full cell. MFCs for EIS measurement were poised at each optimal potential for 30 minutes to make them produce a stable current. EIS was performed at each bias potential with the following conditions: amplitude 10 mV, initial frequency 100,000 Hz, final frequency 0.01 Hz, 10 points per decade of data acquisition. For Coulombic efficiency and energy efficiency measurements, CODS of medium samples taken from the beginning and final batch were measured. When voltage reached 30 mV, MFC operation was stopped and a sample was taken for COD measurement. 2 ml of suspension was taken and filtered through a syringe filter to remove suspended solids, and its filtrate was tested by COD kit to measure its COD. CE was calculated as this. EE was calculated from the ratio of power produced by the MFC to the heat of combustion of the utilized substrate as this. To investigate the effect of each explanatory variable on the response of our interest, we consider linear model. Pmax is maximum power density, Imax is maximum current density, Iopt is optimal current density, Rint is internal resistance, Rohm is ohmic resistance, RCT1 is charge transfer resistance 1. RCT2 is charge transfer resistance 2 and R total is total resistance. Results. Polarization and power density results showed that H1 produced highest power and current. Maximum power density in average was highest in H1, 1961 mW per square meter, followed by V1, 1887 mW per square meter, V2, 1692 mW per square meter, V3, 1672 mW per square meter, and H2, 1630 mW per square meter. Optimum current density is the current density during an optimum operation when an MFC produces maximum power. Optimum current density values in average was in a same order as those of maximum power density. Maximum current density in average was also highest in H1, but their descending order did not match the orders of the other performance data. To figure out an important factor on power and current generation, slopes of polarization curves of anode, cathode, and full cell were analyzed. Internal resistance was calculated from a linear part of full cell polarization curves, and it showed that Rint in average was lowest in H1, 74.0 ohm, followed by V1, 84.5 ohm, V3, 88.5 ohm. V2, 89.5 ohm, and H2, 95.5 ohm. Internal resistances of the MFC were proportional to their power densities and current densities, but electrode polarization resistances were not. For more accurate analyses of electrochemistry, EIS was employed to an anode system and a full cell system. The change of anode configuration greatly influenced the change of anode impedance. Specifically, its effect was greater on anode charge transfer resistance than anode ohmic resistance. Anode ohmic resistance was affected by the anode configuration change, but their contribution to total anode resistance were not significant. Anode charge transfer resistance and total resistance in average were lowest in H1, followed by V1, V2, V3, and H2. As the distance between the anode and the cathode increased, both the ohmic resistance and the charge transfer resistance of the anode also increased. This result showed anode charge transfer resistance is a dominant part in the total anode resistance. The change of anode configuration also greatly influenced the change of full cell impedance, and full cell EIS showed the same trend as anode EIS. Full cell ohmic resistance and charge transfer resistance were decreased by 82% and 49%, respectively, by merely changing anode configuration in a single-chamber cubic MFC. Ohmic resistance and charge transfer resistance of the full cell were closely correlated with the distance from anode to the cathode. Coulombic efficiency and energy efficiency measured to investigate the effect of different anode configuration on Coulombic and energy recovery efficiencies. The H-type cells showed relatively higher Coulombic efficiency, energy efficiency, and COD removal rate and shorter batch time than those of the V-type cells. On average, Coulombic efficiency was 25.1%, energy efficiency was 8.9%, COD removal rate was 10.0 mg per liter COD per hour. COD removal ratio was 96.3% and batch time was 61.8 hours. We explained the 7 full cell responses regarding each explanatory variable. Notice that the full cell responses are well explained by each of 3 explanatory variables, Ca, F, Fa, respectively. Regarding maximum power density, optimal current density, internal resistance, ohmic resistance, charge transfer resistance 2 and total resistance. The same variables are statistically significant at the same cutoff value. Discussion. It was found that average distance from a core rod to the cathode, Ca. Average distance from carbon fibers to the cathode, Fa, and closest distance from carbon fibers to the cathode, F, were significantly important variables in explaining electrochemical responses of the MFC. However, F might be a misleading variable because certain parts of the carbon fiber may vary in length. Therefore, it is reasonable to consider Ca or Fa as a statistically significant explanatory variable in understanding MFC electrochemistry. The charge transfer resistance contains a anodic resistance related to the transfer of electrons and charges in respiration of anode biofilm community. Because as the distance between the 2 electrodes decreased, the amount of current increased and the energy obtained by the anode biofilm increased. In this case, decreasing electrode distance could make respiration of anode biofilm faster so that anode charge transfer resistance could be reduced. Coulombic efficiency and energy efficiency are indicators of energy recovery, and COD removal rate is an indicator of organic oxidation rate. So, it shows that placing the anode horizontally on the cathode is advantageous for energy recovery and organic wastewater treatment. We tested a separator in all the other settings and found that separator utilization there lowered power generation. A separator in the H1 configuration surely improved power generation because it prevented a short circuit. So, we can conclude that the H1 configuration is the best anode configuration for power generation in the single-chamber cubic MFC. Conclusions. Distance between the brush anode and the cathode appreciably affected MFC performance and internal resistance of an anode and a full cell. By merely changing anode configuration, maximum power density increased by 20% and optimum current density increased by 30%. The optimum configuration for maximizing power generation was the H1, the horizontal anode configuration with closest electrode distance. The center of a titanium current collector and the center of carbon fibers of the brush anode were found statistically significant reference points for explaining MFC electrochemistry. The presentation is done. Thank you for your attention.